Okay, good evening, everybody. Thank you for attending this evening's webinar. We are very lucky to have Adam Jordan who is the Asia Pacific lead from Bryden. He's actually based in Australia, and he'll be talking to us about digital workflows for DfMA, and talking to you about computational approach. Okay, that will include information sharing, collaboration, and digital to fabrication. Okay, after that, we will have also Ling Ban Liang from SUTD, who's actually a research fellow based in Singapore doing computational approaches for sustainability. He will share with us on optimization of residential buildings. Right, so without further ado, I will get Adam on board, and all yours, Adam.
Fantastic. Thank you very much.
Right.
So let's just share my screen. And get started.
All right.
Okay, so thanks very much. So there's a fair bit of content here. I'm going to try and get through it all in the time and make sure we have a few minutes left at the end for a couple of questions. But look, there's a lot of these projects. There's plenty more information on our website, and also and also a lot of other literature to look at if you're interested. And of course, at the end of this, my contact details are there. If you have further questions that we don't get a chance to discuss, I'm very happy for you to reach out. It's a pretty broad topic, and it's kind of hard to cover in kind of 20 or 30 minutes. Digital workflows for DfMA is kind of a fundamental aspect of what design for manufacture and assembly is for us in Bryden. And I'll talk a little bit more about our philosophy as we go forward. And I want to show you a few examples and kind of make it real and show you kind of how that workflow was executed on specific projects. I'll just introduce Bryden quickly. So yeah, my role is the Asia Pacific lead. I'm based in Australia. I was in Singapore for a few years. I set up the Singapore office of Bryden, which is still there today. And my role is to run that office still, but also our wider work in Asia. So when it's not COVID times, I'm coming to Singapore all the time. I'm always very happy to support BCA and also IHLs in Singapore, obviously, and invest in kind of the students and the workforce of tomorrow, of course. That's a philosophy that exists across our practice, and we do that a lot in Europe and the UK too. We have about 250 people, mostly in Europe and the UK. In Singapore, we have our regional headquarters. And we're multidisciplinary, so architects, engineers, structure, civils, mechanical, electrical, also a lot of other kind of specialist disciplines, and a lot of creative technologists, mathematicians, digital designers, industrial designers, a lot of different quite technologically kind of capable people working using digital tools to drive better results on our projects and trying to improve the way that we deliver projects too. And everything that we do is obviously to achieve a better built environment for clients and for builders but also for the general public who use the spaces that we design. It's kind of our core philosophy. So we're always trying to find the best constructible solution to deliver the outcome the client is looking for, kind of without compromise. So that means we don't want to kind of force a particular construction solution on a client. DfMA is all about designing a building so that it can be built in the most constructible way. So the D stands for design, but I also kind of think the D in some ways it's all about data, because this design with a focus on constructability, you need to understand how buildings go together, and you need to understand how they're assembled at a very early stage, much earlier than you would in a conventional project. And so it means that you need information, and you need to collect and accumulate and aggregate and then exploit information about buildings. And that's where digital tools are really important, because in today's world, we have this big ethical crisis of climate change and environmental challenges that mean that the conventional approach to construction doesn't really work anymore to deliver the kind of results that we need it to. And Singapore has its own challenges around labor productivity, but in every country there are resource issues, and there's also the increasing demands of the construction sector. So we need to find ways to make construction more efficient, and designing for manufacture and assembly to build buildings in the most efficient way is a way to achieve that. But we also have this unique kind of opportunity because digitization in the construction industry is accelerating at such a rapid pace. And the capability of the tools and the software that we have at our disposal is beyond what we could do even a few years ago, and it's changing all the time. We've done projects like Crossrail down here, I'll show you in a minute, which we just couldn't have done even a few years before we did it. We didn't have the tools to do what we did now, and that's always evolving. So it's very exciting, actually. All of a sudden we have this great opportunity to use data and to design with data and to design with knowledge and inform our built solutions more efficiently from the very earliest stages. So we're very materials agnostic, lots of kind of different materials here, timber and steel and concrete and bricks and all sorts of things. Lots of different methods, so some like PPVC type of buildings, but a lot of flat pack and cassettes and components and that kind of thing, and bracketry and all sorts of different types of sectors. So railway stations, this is for a prison, this is a hospital, this is an airport, that's a classroom, that's a house. That's a wastewater treatment plant, so lots of different sectors as well. And everything has this fundamental philosophy that a building is comprised of a kit of parts, right? We have this common thread of a kit of parts. The buildings can be broken down to their constituent elements, and we apply standardization at those component levels to try and find customized site-specific building designs that are assembled using standard components, kind of like the chassis of a car, all these different standard components that go together to form a lot of different models and a lot of different variations, but using that same standard kit of parts to drive manufacturing efficiency, mass production, and customization of the end result. So I'll show you a few examples, and I wanted to talk about how we design digitally. What does it mean? How do we even start? So the first point is that a DfMA provides rules. So designing for manufacture and assembly is all about setting rules and a structured approach to both relations between elements of a building, so how the kit of parts goes together, and also the overall geometry. So the more we define rules, the more we can digitize, because digital software is all about applying rules to generate an end result. So there's kind of an industry standard, which is BIM, and it's been emerging for probably 10 years or more now. We were quite pioneering in the UK in BIM adoption, and now it's increasingly an industry standard. And BIM is a big shift, so it's all about designing with data rather than geometry. The hand drawing or AutoCAD, this kind of approach is very much about the geometric representation of the building. But BIM is about the parametric content of the BIM model is kind of more important than the picture. It's more important than the fancy 3D model you get. The real power of BIM sits in the parametric content rather than in the geometric. A structured approach to developing that data in a step-by-step manner across the whole life cycle of a project is really important. So BIM is also not just a single software. So a lot of people think that BIM equals like Revit, for example. BIM is actually a workflow. So there are software tools that can operate in a BIM environment, but a real BIM project isn't just about a single platform. It's about different softwares working interoperably together, and each customized to deliver an end result. So different users will need different types of files and different types of models to use in different ways, and mapping up that interoperability throughout a whole project, and also considering the functions of the different software platforms at the early stage is really critical. So a BIM project becomes something that's really set up from the start how you expect to proceed, and it's a very front-end loaded activity. And a DfMA project really has to have a very close eye to what the end result is going to be, what the link to fabricators is going to be, what the link to the DfMA kit of parts is going to be. I can provide these slides to you as well afterwards, and you can feel free to have a look at some more of the detail on here in your own way. Data exchange file formats also need to be considered. So how that information goes between one software platform and another, and then how you actually access that information. So is that using a common data environment, online, a kind of cloud-based collaboration platform, a CDE, and how different users in different locations, potentially even different countries, are accessing not only the geometric representation of the model, but also that data that sits at the heart of it and is kind of the most important part. So today, BIM is the kind of technological paradigm of our whole industry. It's like the center of the industry increasingly. In Europe and the UK, BIM has gone to kind of being the minimum standard, the minimum requirement on projects, but it only gets you so far. So we want to start to exploit what BIM provides rather than being constrained within that ecosystem. It's supposed to be a tool to kind of liberate our design process. So we have this idea that BIM is actually kind of only part of a wider digital story. There's all sorts of other tools, geospatial analysis, mathematical modeling, algorithmic design, generative design, the Internet of Things, virtual and augmented reality, and digital manufacturing tools, and probably others as well. And this is more like an ecosystem of softwares that has always data at the center of it. So what we're doing is using the tools at our disposal to use the data about how buildings are designed and go together to deliver the best result at the end of the day. And the more we can widen this circle to embrace other elements of digital technology, the more we're going to be able to design and deliver buildings both faster and smarter. Instead of doing them a bit faster, but in a pretty similar conventional fashion, instead of doing it kind of a different way, but just as slowly, we think DfMA is about delivering better results with accelerated time. And that's where kind of design automation begins to play a part as well. So we're not interested in taking the job away from designers. We are designers. We want to liberate our time to focus on where we really create value, which is really kind of in 10% of the work, and 90% of our time is spent doing details and kind of door schedules and things like that. We want the computer to do that, and we want to be able to focus our time on the construction system and thinking about how the buildings go together in the most efficient way. And that's where we can use our intellect and our thoughts in developing the design that works. And then this kind of stuff, the routine, repetitive stuff, is delegated, and that's an automated design approach. So I'm going to show you a quick video about coming back to this topic of automation and a DfMA outcome. So this video here, but I'm not sure you can hear it anyway. It's an app we designed for this, find it online, and it's open source. The automated app allows users to in minutes, designed for the housing block in London. So you can select the DfMA system you want to use, and all of the code and statutory compliance requires coded in, so as basically a rule set. So it's kind of takes the user time to develop it. Then you can get a lot of statistical analysis out of it when you have to export it into Revit or into the data into schedules, CSV file format that you can then use to further develop the design. And that app was developed together with a lot of industry partners and a lot of manufacturers as well. So a lot of the components in that app are DfMA manufacturers in the UK, and the idea is it will ultimately become a digital marketplace for DfMA buildings that you can very quickly get a direct link to suppliers, and they've inputted into the design of the system so that you know that this building of this layout and this configuration will meet the client requirements, will meet the government requirements, and will also be buildable from these manufacturers, and we'll have an idea of what the price is. So that's a very exciting development, which is really, I think, the first of its kind in the world and a pioneering approach by the Mayor of London's office. So I wanted to talk about this other example of Crossrail and explain a little bit the kind of fabrication link. So in this project, we used, this is very much a DfMA project, but also a digital automation project to achieve something very challenging. Oh, and this is really not a fancy kind of grand sweeping gestures. It's more about the control and the precision, right? So we spent a lot of time, this is all about the tunnel linings of metro state, like MRT stations, like the cladding panels inside tunnels. But there was a lot of them. It was kind of many kilometers of these, and they were all quite different, actually. So we spent a lot of time on standardization and minimizing the number of fixings per DfMA bay. So each one of these is a prefabricated bay, and we spent a lot of time optimizing that bay. And then built essentially a digital twin, so a very highly detailed spatial model, and actually in SolidWorks, right down to a very fine component level of detail. And there's a huge degree of design automation in this, particularly in things like positioning, bracketry, and screws and perforations. It would have been an incredibly laborious effort to build this model manually, so we used the design automation to do it for us. And then we took, as the tunnels were formed by the tunnel boring machines, we took like point cloud surveys, and then we overlaid our digital model onto the point cloud model to check for fit and tolerance, and we made adjustments to the model before the elements were fabricated to make sure that they would fit, and sometimes we made adjustments to the tunnel walls themselves as well to make sure they would fit. Once we had the model working well in the tunnel, we made it, and it was GRP, and this is a mold, so very large molds. These are very, very large elements actually, but the molds are formed directly from the model, and then fabricated. So here's the element that mold is from being fabricated, and other elements too, fabricated and stored directly from the model, and then delivered into place. We spent a lot of time working on the model, making sure that we had adequate delivery routes and that we could get access to the platform in every location. And finally, the end result was very successful and minimized the amount of time that people needed to spend in the tunnels fixing defects and adjusting and making adjustments and alignment and all that stuff. So the benefit of this was really making the site work very rapidly and very efficiently by maximizing the amount of work that we did off-site in the office. Another example of a kind of an end-to-end digital workflow was this mixed-use development in Edinburgh in Scotland, a 1.7 million square foot development, and this is quite a sophisticated modeling project we did with Lang O'Rourke. So we had a direct connection with their fabrication team, Explore Digital, and I'll explain the way that worked. So we worked very closely with Lang O'Rourke as they were our client. So we modeled each individual cladding panel to a fabrication level of detail and also a fabrication level of information. So they had the data attached to them that defined it to a high level of detail, including all bracketry. And this became a real digital twin model, so structurally performing as it should. And then we used the model to schedule the components out directly for procurement, for pricing, and for procurement with the fabricator. So we used a bit of bespoke Dynamo scripting here to position stone panels across the facade. So 19,000 individual stone pieces at 10,000 square meters of stone, and all of them positioned according to the Dynamo rules, which were based on the architectural requirements from the concept design team of the project. We also developed we also used the model to do other things like a crane utilization strategy. So we knew the tower crane positions, and we assigned every panel to a different tower crane based on its location in the overall building. And this is also using Dynamo. So this allowed us to see if there were any panels that were not easily installed by one of the tower cranes that was on site. And just I skip past this quickly, I'll just come back to it for a second. So we used Dynamo a lot in here. The basic model was Revit, but developed to a connections level of detail. We use an IFC file format to export parameters from the model to PlanBar, which is the fabrication software, and that workflow was tested by with Explore Digital, who were the fabricator forerunner, and ultimately fabricated very, very much through the model with no drawings. So that was a very efficient way of designing that building. I think just one other quick example here, and then we'll have a few minutes of questions. I wanted to show you something a bit different. So we have a design system called Platforn 3 in Bryden. It's a DfMA design system. It's a very rapid way of building a steel and concrete superstructure frame. It uses automated construction techniques to assemble it, and we kind of had an idea that this would be much quicker on site, but then it's one thing to test that in a model, and it's another thing to test it in the real world, where you have a lot of challenges from wind and rain and people calling in sick and things like that. So we wanted to use a digital simulation tool to test and optimize it before we actually went ahead and physically prototyped it. So we developed this model, and I'll just talk you through how it works. So we have a lot of inputs, so we can set the number of workers we have on site. We set the shift pattern if they're working overnight or 24/7 or whatever. We set the location and the year. The time of year when it starts. And there's an interesting feature here because we picked London, Singapore, and Hong Kong. Because if you build in London in winter, you have to stop construction sometimes because it gets cold. If you build in Singapore, sometimes there's heavy rain and it causes a delay on site. And if you build in Hong Kong in typhoon season, you also have to shut down the site. So depending on the time of year you start and the location, you can have shutdowns. So we built all that into the model. We built in a lot of other inputs like install times, all based on what we thought the outcome was going to be, but we had sliders so you could be more positive or like pessimistic or optimistic with your estimates. And then the minimum and maximum temperature when you want the site to operate, and the maximum rainfall, how often you think the worker will call in sick, how often you think the equipment will break down. And then we run the model. I'm just going to run the model very quickly. You can see it's a very quick thing. This is using a platform called AnyLogic. So it's basically a rules-based simulation engine. That's very, very, very sped up. It's already finished, actually. I can run it even again because we have a little bit of time. You can see how quickly it's sped up here. But this is a simulation based on all those rules of exactly how long it will take to form that kind of only concreting the first floor, the second floor, but a single bay. And then you get all these outputs, a lot of statistical outputs about kind of how many days of shutdown you had, how productive your workers were being, what your installation times were, how productive your different pieces of equipment were, and also how many workers you had and what their wages were and how much operational cost you had. So with this data, we can then not only we can optimize the system and we can go back to the DfMA system and refine it and start to understand it better and make small iterative improvements that deliver a lot of benefits in the long run. But we can also proceed to physical prototyping with a much greater level of confidence in the design that we've developed and the fact that it will actually work in the real world. And at the end of the day, the DfMA solution is the one that is the most efficient way to build a building in the real world. And so the more we can use digital tools to make a virtual world as close as possible to what will happen in the real world, the better a result we're going to have and the better projects we're going to be able to deliver. So that's my presentation. I hope it was an interesting, if very quick overview. And that's my contact details there, but I'm also happy to take a couple of questions if we still have time.
Yes, please feel free to ask any questions that you have with Adam. Just to check with you, Adam, the software that you mentioned just before, I think the last two slides, if I'm not wrong, the one that shows the simulation of it's like a timeliner sequencing, right? Um,
Of
the one
of
that,
this,
the,
this
yes,
one.
this, yeah,
Mm.
the platform tree is it's not a free software, right?
Um, I think there is a free version. I think there is a trial version which
Mm-hmm.
has limited functionality. It's actually a fairly expensive piece of software.
Yeah.
And actually, this is a very unusual application for this software. This was developed for industrial process projects, and we do a
Mm-hmm.
lot of like pharmaceutical work in Singapore. So, for example,
Okay.
AnyLogic is used a lot for planning supply chains
Okay.
and movement of logistics between different factories, so movement of materials from one location to another
Mm-hmm.
by logistics companies, shipping companies, also factories that are manufacturing products with raw materials or sequencing deliveries of their finished goods from one location to another. So we use the platform for a slightly innovative purpose in this case because we happen to have people in Bryden who have the
Mm-hmm.
experience with it. Um, I would suggest that I think for the average person seeing poly, it might be a bit of a step to kind of learn something like this. It's more like showing you the. I'm just trying to create some, maybe give some inspiration or something that
Mm-hmm.
you kind of think about buildings in this way and use digital tools to simulate how buildings go together
Yeah.
and really it's about testing. It's about testing and validating it because it's one thing to say that something works in theory, but it's another thing to kind of prove it,
Yeah.
and that's really valuable to us if we can say
Mm.
to a client that we know that this works because we've tested it. They're the ones who need to pay for the project in the end. They're the ones who are going to make the investment. So if you can give them confidence, then it takes a lot of risk away and it takes a lot of uncertainty away, and it means that you have a much more successful project in the long run.
Right. Because at this point, when the students are working on this sequencing construction timeliner, they actually
Mm.
use Navisworks, which is also part of the Autodesk,
Yes,
right?
of course.
So yeah, they could simulate the construction process as well. So that is actually included in their free educational license. So that was what actually we are using at this point.
Yeah.
Mm-hmm.
And Navisworks is a great tool as well. And the phasing capability in Revit
Mm-hmm.
will give you together with Navisworks quite a powerful tool.
Mm-hmm.
It doesn't go. I think it doesn't build uncertainty in quite the same way that this software did. So the reason we had this software was that if you have a phased model in Revit and you export it to Navis and you run that sequence, it will be exactly the same every time. But
Mm-hmm.
if you build a building in the real world and you build the exact same building 5 times, it will be different every time because you have some traffic and you have some rain and you have some people
Mm-hmm.
sick and you have something takes a bit longer than you expect it to. Always on a building site, there's always some uncertainty. So this model is a way for us to kind of test that uncertainty and see what out. So if you run this model, every single time you run this model, it's like it gives you a slightly different result
Right.
because it factors in that uncertainty
Mm-hmm.
factor the existing conventional modeling. So yeah, for us it was a very useful insight, I think. But you can get a long way in testing a system with Navisworks.
Sure.
So I'll just put my contact details up again one last time and say
Sure.
thank you
Thanks.
again.
Yeah, correct. If there is no other questions from the floor, thank you, Adam, for sharing with us. A very insightful thing on DfMA.